Alright, Bismillahirrahmanirrahim. Let's go for the real beams in real life, the SIB. The loading on the floor beam used in the airplane is shown. Use disconnected functions that determine the reaction at the support EMB, and then draw the movement diagrams, and you can also draw the SFT, the structure also. Now in this, it's an open-ended problem because they are not giving you any cross-sectional details of the specifics. We can assume our own, but remember you have to assume a logical cross-section, otherwise results will not be as per the what is given in the RC Hibbler. Okay, so the assumption has to be logical, and you can have variable results, it doesn't matter, but as long as you know how to solve the problem, that is the real thing. So we start with here we start up with the structure solving. uh, let's go for the preferences. We go for the structure, and we write OK. Then we go for the preprocessor. We have to select the element. So for the element, we basically go for beam to node it 188, and we close it. Then we go for the material properties. It is an English gear system. So structural, linear, elastic, isotropic. We write 29E6. Here we write it as point. Okay. And we close it down. Then we go for section. For the beam, the common sections, here this is an assumption phase. We write it as 24, and we write it as 12. You get your eyes entered as this value. Apply. OK. And basically, again, this is we go for the structure building, modeling, create key points in active exponent system. Apply number 2 as 120 inches. Number 3 will be 240. Number 3. Why you put 3 here? This is here. 1, 2, 3. So now we need to create the lines. Lines will be straight from here, here, and from here to here. We apply and plot the lines. The lines are here. Then go for the meshing, size controls, manual size, global, and we write it edge length as EL as 100. Again, it's a variable thing, variable assumption. You have to make it 150, you can make 50, seeing the result convergence. So this is basically you have to assume with experience. Then you write it as recall. The lines have been meshed, so it's one single structure now. Plot, replot, plot elements. So now we have to apply the loads. Plot controls, numberings. to apply the loads by structural displacement on key points only y and here wall dual make it 0. Okay. You can write plot the elements here. Right. And then if you want to go for the pressure on the beams, look at the box structure. Box 2, the pressure is 30 pounds per inch. Wow. See, it's been done. Then we basically go for the, we have constrained it, and then we go for the solution. Let's see if it solved it correctly or not. It has done it. Let's see the plots. These are all the respective outputs that have been generated. Okay. So now see the deformation. It has to be low. Plot results. Deformed shape. So this is the deflection in inches. It was 240 inches long beam, which is 0.0005 of an inch, which is very good. We have modeled the deformations are very small, and that is what we really wanted for our results. And the listing of the results, go over direction solutions, and see if you got here is as node 1 433.6 pounds reaction at the roller, and the last one is 3166, means 3.16 kilopounds of an inch. Okay, and this is 433 pounds. So if you look at the solution, this was AY 394 pounds and BY was 3.21 kip. So our is 391, here it's 433 pounds, and this is 3.1 kip, this is 3.16 kip, which is very good. So we have converged it very well, and the movement is if we write is 111.9 kip, 111.9 kip, and what was the actual Hibbeler? 122 kip. So this again we have assumed many things over here, but we have come at very close, which is a very good solution, because Hibbeler does not give us all the values, all the points, and he has not given us any information about the material. It can be any material, aluminum or anything, but we have assumed those values. We have assumed the material, we have assumed the cross section, and still we are able to get so close to the convergence, which is very good. So we can go further. Here is that we can make it an isometric, and we will be interested in plotting the elements and plot controls, numbering style. We go for size and shapes. We close this up and we say we want the elements to be displayed. So here it is, and then we can say that plot controls, contour plots, element solutions. If you are interested in calculating the energy, the strain energy of the structure, very good if you want. This is the strain energy, very low strain energy, because the value of the force is very low loading. So 0.22, which is almost very good. It cannot undergo any deformation. It is very stiff. So if you want a nodal solution, displacement vector sum, this is the nodal solution. If you are interested in basically the rotations, the slopes of the structure, so again it is very, because the deformation is very little, so the slopes is almost very negligible, which is again very good. And if you are interested in also calculating the, you can get other things also. If you are plot the elements, and you are interested in further calculating the shear force bending moment diagrams, you have to define the table. Go here, add again this. Still now the results are very good. 3, and you apply 16, then 6, then apply the 19. There it is. Now you are interested in the plot results, the line element results for the PMD 3 and 16. It will be something like this in 3 dimension. It's trying to tell you. You can always go like this and pan and rotate and make it different. And for the other way, if you want, just close it out, and you want it 6 and 19. 6 and 19 if you want. So this will be similar to that for the SFP. And if you want plot elements, if you are interested in the deformations, contour plots, plot controls, animate deform results. So if you want to use some, so here it is the use some. This summing means UX, UI, UZ on all 3 dimensions. And then if you want, you can stop it, close it, and again you go for the plot controls, animate the deformed results. You are interested in the rotation sum. You can imagine it's very low, because the load is very low and the beam is very large. So the deflections and the strain energies will be very slow. It's very logical if you apply the concept, actual logic. So you can get further results as you want for the animation. These are the principal stresses. Again, very low value. You can see it's all bluish. So design was very good. Plot controls. If you want to understand the deformed shape, deform plus undeformed. So it is like here, it's coming in better loading. So I hope how to solve analysis. It's just a simple methodology to give you an example how to do it in your real structures, and it gives you basically all the data which is required, and it gives you the listing of the results also, the nodal solutions and everything. And the movement like it is was MZ, moment about Z, was 0.119 E6, which means 111.92 E3. So like here the moment calculated by Himmler was 122 kiloponds inch. So that is quite good. So I hope this will be make you interested and give you an initial idea how you solve it in Ansys, and basically it will help you in your CEP quite well. I hope. Thank you.